Hello, fellow students. Today we're going to talk about relations within graphs, and specifically about the equivalence and order relations. So stick around and enjoy yourself. Okay, so this is the problem for today. We have a directed graph defined here. And as you can see, we have the set of vertices, the set of edges, and the application, right? And we have the application defined here for every link in the graph, for every link or every edge, right, in the graph. Then we have two questions. Does it represent an equivalence relation and an order relation? Just to remind that an equivalence relation means that the graph meets the properties reflexive, symmetric, and transitive. Okay, so the reflexive relation means that a vertex must be related to itself, right? There must be a link, a loop from a vertex to itself. The symmetric relation means that if the vertex A is linked to the vertex B must be as well linked back to A. And finally, the transitive relation means that if A is linked to B and B is linked to C, A must be also linked to C. Right? So this is the equivalence relation, and then we have the order relation. Right? So in this case, it must meet the properties reflexive, antisymmetric, and transitive. Okay, so antisymmetric is the opposite of symmetric. So for the antisymmetric, if A is linked to B, B must not be linked back to A. Okay, so the best way to work is with the adjacency matrix or the accessibility matrix of the first order, right? So the best way to check this is with the adjacency matrix or the accessibility matrix of order 1. So let's calculate the accessibility matrix of order 1, right? So if we start by the first position of the matrix, we can see how the first vertex is accessible from the first vertex, right? This application says that the vertex 1 is accessible from 1, right? Because we have the loop A there. So we put a 1 in the first position of the matrix. Then this is a directed graph, right? As you can see, we don't have any link, any path of length 1 from 1 to 2. So we put a 0 here. We don't have any path of length 1 from 1 to 3. we don't have any path of length 1 from 1 to 4, and we do have a path of length 1 from 1 to 5, right? So we put a 1 in the position 1, 5 of the accessibility matrix of order 1. So we go to the second row, and we have another path from 2 to 1, right? Path of length 1 from 2 to 1. So we put a 1 here. We have not a path of length 1 from 2 to 2. We don't have from 2 to 3. We don't have from 2 to 4. And we don't have from 2 to 5. We go to the third row, third vertex, and we don't have from 3 to 1. We don't have from 3 to 2. We have from 3 to 3, right? We have a path of length 1 from 3 to 3 because we have an edge from 3 to 3, the edge F. We don't have from 3 to 4, and we don't have from 3 to 5. So we go to the fourth row, and we don't have any path of length 1 from 4 to 1. We have a path of length 1 from 4 to 2, right? We don't have any path of length 1 from 4 to 3. We don't have from 4 to 4, and we don't have from 4 to 5. We go to the fifth row, and we don't have any path of length 1 from 5 to 1. We have 1 from 5 to 2, right? It is defined here. We don't have from 5 to 3. We have another path of length 1 from 5 to 4, right? And we don't have any path of length 1 from 5 to 5, right? So this is the accessibility matrix of order 1. Okay, what happens here? Let me check the line, color black. Okay, so this is the matrix. So let's check the properties on this matrix. Okay, so the reflexive means that every node must be linked to itself. And this in the matrix, this translates to have ones in the diagonal, right? The elements in the diagonal must be 1. So in this case, it is not reflexive because we have zeros in the diagonal. For instance, in the position 2, 2. Okay, in these positions we have zeros in the diagonal, so it is not reflexive. We check the symmetric property, and in this case, in the matrix, this means that if the element, for instance, 1, 2 is a 0, the element to 1 must be also a 0. Right? In this case, we see how this matrix is not symmetric. So we write it down. Matrix must be symmetric. And it is not, right? For instance, remember that we have defined what is a symmetric matrix in one of the first exercises, right? For instance, the element 1, 5, right, is equals to 1, and the element 5, 1 is equals to 0, right? The element 1, 5, it's equals to 1. It means that there is an edge from the vertex 1 to the vertex 5, but, well, an edge, I mean a path of length 1, but there is not a path of length 1 back from 5 to 1, right? So the matrix is not, and the graph is not symmetric. And then let's check antisymmetric. So it means that for each element out of the diagonal whose value is 1, the symmetric position must be 0, right? So it is the opposite of symmetric. So let's mark these elements in the matrix, right? As we can see, for the symmetry, let's mark them. Okay, why is this line so thick? Okay, it's this pen. For the symmetry, right, we can see how there are elements like this one, that are not symmetric. And now for the antisymmetric, we need to check if for every one that we have in the matrix, we have a 0 in the symmetric position, right, outside of the diagonal. Okay, so in this case, let's continue checking, right? So for this one, we have a 0 in the symmetric position, right? Let's mark it in a different color. For this one, which is in the position 4, 2, we go to 2, 4, 2, 4, and this element is also a 0. And for this last element, which is in the position 5, 2, 5, 2, we go to 2, 5, 2, 5, and it's also a 0, right? So we have checked, and for everyone in the matrix, there is a 0 in the symmetric position, right? So in this case, the matrix and the graph are antisymmetric. right? Yes, we have checked every element with every element Mij equals to 1 in the matrix, and Mji is equals to 0 when we are not in the diagonal, right? When I is different than j. Is different than j. See colored elements in the matrix. Okay, and the last one is the transitive property. To check if the matrix is transitive, we need to check if the accessibility matrix of order 2 is contained or is included in the accessibility matrix of order 1. So in this case, we need to calculate the accessibility matrix of order 2, right? We need to calculate this matrix, and as we have seen before, we only need to multiply the logic multiplication, right? Of M1 by itself. Okay, so as we have done this already, right? I will do it quickly. So we multiply the first row for the first column, and we get a 1. We multiply the first row for the second column, we get another 1. We multiply the first row for the third column, we get a 0. The first row for the fourth column, we get a 1, and the first row for the fifth column, we get another 1. We go to the second row, we multiply the second row for the first column, for the second column, for the third, for the fourth, and for the fifth column. We go to the third row, and we multiply it for the first column, for the second, for the third, for the fourth, and for the fifth column. We go to the fourth row, we multiply it for the first column, for the second column, for the third column, for the fourth column, and for the fifth column. And finally, we go to the fifth row, and we multiply it for the first column, for the second column. Sorry, there's a 1 here. For the third column, for the fourth column, and for the fifth column. So finally, we have the matrix. And as you can see, there are elements which are not contained, right, in the accessibility matrix of order 1, right? So for instance, this one, right? This one is not here. This one is not up there. Right, and a few more elements, right? These 2 ones are not there, and also this one, right? All these elements are not contained in the accessibility matrix of order 1, right? So it is not included, right? For instance, the element in the position 1, 2 is 1 in M2, and the element in the position 2, 1 is 0 in M1, right? So it is not transitive. Okay, so finally, we have checked all the properties, and let's write the answer, right? The answer is, to represent an equivalent relation, it must be reflexive, symmetric, and transitive. And it is none of them, right? So it does not represent an equivalent relation. To represent an ordered relation, it must be reflexive, antisymmetric, and transitive. It is antisymmetric, but it is not reflexive and transitive. So it does not represent an ordered relation. Okay, so this is the exercise for today. This was it. I will stop sharing the screen now. Okay, let me check. I will let you a few seconds to check the final solution, and I will stop sharing the screen now. And the next day we will continue reviewing what is a total order relation and doing the second part of these exercises. So I will see you on the next day. If you have any question, as always, don't hesitate to ask in the comments. Okay, so goodbye, nice to see you, and see you on the next day. Bye-bye.